like the first exercise in this chapter, we're facing a similar problem, especially when we come to the last one here, D. But here we have three individuals, Alice, Bob, and Carl, arranging a meeting for dinner. They arrive independently and uniformly distributed time between 1 and 1:30 p.m. that day. And so here we first asked, what is the probability that Carl arrives first? So just defining the random variables A, B, and C independently, uniform between 1 and 3 p.m. I'm going to now just standardize this, so it's going to be between 0 and half. That was ugly. Half, like so. And half means that we have, well, we can do actually just write it down as 30 minutes, just to make it a little easier to think about it, and then I'm going to standardize it. But we have here 0 meaning 12, and it will be, this is half, 0, 30 minute, like so. So we don't need the actual distribution at the moment. We only need to understand for the first exercise what it means that Carl arrives first. So I'm going to say Carl first, like so. That means two things. The probability that Carl arrives before Alice and before Bob, but also that the probability of Carl arriving before Bob and then before Alice, those are equivalent. And now, because things are uniform and independent, the probability that this event happens is 1/3. I mean, it is basically what this is saying. I mean, that we have a naive definition of probability. Everything is equal. So C being in this position or that position or this position is just 1/3. So this arrangement here is just 1/3. And the same with the other probability. Okay, and then that leads to actually, I just realized I made a mistake here, which is that it shouldn't be 1/3. It's actually 1/6, because what I said is that all arrangements here, right? So it should be all types of combinations, and we have 6 of them, and this is 1/6. That is 1/6. Okay, and those lead to 1/3. Okay, so just to clarify that we're basically saying that by symmetry we have that type of arrangement across the different events that can happen here, and that is why this particular one is 1/6. If we type up all combinations here, we'll see that where order matters, that we'll have 6 of those events. We're interested in one of them, and also this type, which is the second one. Okay, hope that was clear. And the other question here now is that we're told that what is the probability that Carl, well, first of all, for the rest of this problem, we're assuming that Carl arrives at a certain time, 1:10 p.m., and we're going to condition on this fact for the rest of all of these. So here, then we ask what is the probability for Carl's waiting time being more than 10 minutes. Okay, so here, and let's state the fact that because now Carl, I'm going to draw this timeline again. Carl arrives, so this is 12 p.m. and now he arrives. Let's see, so I'm getting this. Oh, sorry, I'm splitting up, confusing 1 p.m. with 12 p.m. from the first problem here. So this should be 1 p.m. 1 p.m. like that, and this is 1:30 p.m. So let's just forget about this definition here as well. It's a little confusing. And Carl arrives here, 1:10 p.m. This is Carl's arrival time. Now we're told to condition on this, and we know that he also arrives first. So therefore, because we're conditioning on this, we're saying now the distribution of A and B, I'm going to redefine them. If you really want to be careful, you could put A star, B star, just to say that, to separate out from these definitions up here. I'm just going to keep this because I'm carefully now in detail telling you what I'm going to do. Because of this conditioning, we're going to say, redefine the domain of this uniform distribution. And what am I going to define it to? Well, if we look at this timeline, we're given the only time that Alice and Bob can arrive is in this interval here, which is that they have 20 minutes to arrive. Okay, and so we are now redefining that region of interest and say that Bob and Alice can only arrive between 0 and 20 minutes. Okay, so instead of 0 to 30, we have now constrained their possible arrival times. And this is critical now, because we can we will be able to also, I'm going to show you visually how to see this in the current setup that we are using. Okay, so let's do the I'm just looking at my notes to see that everything is clear here. And yeah, okay. We have then the following, right? And then we are asked, sorry, I'm jumping a little bit here. So we were asked, what is the probability that he'll be waiting more than 10 minutes? More than 10 minutes. And so more than 10 minutes, so 110, this is half the region. So we have, this is half the probability, and that is the other half. And B, we asked, what is the probability that Carl will be waiting alone for more than 10 minutes? Here, we can now visualize this as the following. We have Carl. Well, basically, let's do the following. So we have the probability that Alice, so A, arriving in this region is a half. B arriving in this region is a half. And because independence between A and B, we can take and multiply them, and that gives us that the probability that Carl having to wait alone for more than 10 minutes is 1/4. And so we're relying on the naive definition again of probability. Naive being that, meaning that everything is equally likely, all of those events and combinations. And C, we are asked what is the probability that Carl will have to wait more than 10 minutes until his party is complete. And here, what does it mean that the party is complete? Well, it could mean that A, Alice arrives here, and then Bob arrives. So let's see, it's within more than 10 minutes. So really what we're looking, so there are combinations of arrival times between A and B. Really what the question is asking for is that what's the probability of having to wait more than 10 minutes. So now thinking about, say that they come all within 10 minutes and we take the complement of that, then we get the desired probability. So it's 1 minus, by the same logic as in B, 1/4. So that probability is 3/4. And that is much easier, obviously, to calculate than all those possible combinations of A, B, and B's arriving in different parts of this region. And D, we're asked what's the probability that the person who arrives second will have to wait more than 5 minutes for the third person to show up. But now we're assuming that Carl has already arrived. So the second person and the third person refers to Alice and Bob again. This problem reminds us a lot of exercise 1 in this chapter. So I'm going to write that down in the same way, because we have to rely on integration, and the easiest way to do that is to visually define the regions of interest and then derive the limits. It's really all about getting those limits right. Okay, so in D, we are given that, so we know that I'm going to draw now the same type of figure that I drew last time. So this is Alice's arrival time, and then we have Bob's arrival time. And we had them, there's a region between 0 to 30 minutes, like so, 30, the same, 30 minutes. Now we are given that Carl arrived in the 10-minute region. So 10-minute region. And because this region has happened, we redefine the and so he arrived there, and this means that these regions are not possible. So the blue is possible and the red is things that cannot happen. So you cannot have Alice arriving before Carl and so on. Okay, and here we're asked, let's go back to the question, what's the probability that the same has to wait more than 5 minutes? More than 5 minutes. So again, thinking about the distance between Alice and Bob's arrival time, this has to be larger than 5 minutes. 5 minutes. And we want the probability of this event occurring. Okay, so the probability of this event, and recall that A and B are now, after conditioning on Carl's arrival, uniform 0 to 20 minutes, because that's what they have to work with. and they're independent. Okay, so let me move this like that. Here, I'm going to move this to the right, like so. And what does this absolute value mean? Well, it means that we have the probability of A minus B being larger than 5 minutes. And I'm going to do one thing very soon, which is that I'm going to redefine these minutes into a standardized version. And the other probability means that we have minus A minus B being larger than 5 minutes. Okay, and that means here I'm going to write this in terms of B's, the B term, because that's our sort of y-axis. So this means now A minus B, just rearranging B, and this other term here, oh, not a B, but a probability. And here we have B being larger or equal to 5 plus A. So 5 here means the event of 5 minutes, okay? Now, 5 minutes are in this distribution here, 1/4 has a 1/4 of a probability of occurring. So really these 5s are 1/4 here. Okay. And now I'm going to use these equations to draw out the feasible region of where there is an overlap between Alice's and Bob's arrival time when they're within 5 minutes of arriving. Okay, start with this one. So here we see that if we put B to 10 minutes, which is actually the new 0, then A will be 15 minutes, right? So 10 plus 5, 10 minutes. So let me draw that as green. Oh, let's take another color. Orange, like so. So let's see, where is 15 minutes? And it's 15 minutes in here. Okay. And it will hit when A is 30 minutes. B will be 25. Okay, so 25 here. Like so, and this is the equation B. Well, let's see. Equals B equal to A minus 5. And we do the same thing with the other one, and now we'll have 25 here, and we'll have 15, the same logic here, so it'll be like that. Okay, and that is now B equal plus A. All right, so, and this is the region where they will be within 5 minutes, so they will actually see each other. Now we are asked to find the other region, which is these triangles here, where they actually won't be meeting. All right, so let's look. We'll just define this visually. And so the probability now, continuing on with this, will be the all right, so let's think about the first triangle. So let's look at this probability here means the being right, let me just check. So B being up here and A, and yeah, so we have that and we have that. So the probabilities are basically describing the regions where of interest. So thinking about the first triangle here, we have that the upper limit is, and now I'm going to write this down in terms of, so let's call this the raw minutes. This is the conditional minutes. So conditional on Carl arriving when he did, and then that's actually the 20-minute line, and now that's the 0 line, and the standardized, they call this standardized version would be that this is 1 and that's 0. And this is what we're going to work with in this integral. So 20 minutes, when we're up here, that actually means 1. I'm just redefining the regions in terms of probabilities, because 20 minutes is not a probability, and neither is 30. So here we're moving, the lower region of the triangle is B equal 1/4 plus A, and it goes all the way up to 1. And the CDF is 1 because it's the uniform. That's what I've defined this variable now to. Integrate over B. And then the outer region over A, this triangle moves in this direction, and exactly these definitions hold for A here as well. So it goes in this direction up to 25, which is 3/4, and it starts at 0. 0, 3/4. Now we have the other triangle plus, and that starts. So let's start with the inner triangle. That starts at going to integrate over B first. Density 1. Here we're moving from 0 up to the upper bound being this here. B equal A minus 5. Yeah, so we have 0 because we're starting in the y direction and going up at the upper bound of B. And A now goes from, when we integrate over A, we go from here, which is 1/4. So that's, why is that 1/4? Because that's 5 minutes in. 5 minutes in, which is 1/4 of a 20th of 20 minutes. So 1/4 and all the way up to A. And these are totally symmetrical. So I'm going to calculate one and then leave the other one as it is. And we can just take this value of this integral and multiply by 2. All right, so I'm going to plus 1 like so. Take the inner integral, so that's a b. We have 1/4 4th plus A 1 into A 0 3/4, and that is 1 minus 1/4 minus A dA 0 3/4. This is let's see, this is 3/4, like so. So we're going to then take 3/4 A minus half A squared. Just taking the integral now, so 0 3/4. These are just continuing on, like so. Now we have 3, so 3/4 times 3/4, that's 9/16, and minus a half, and that's the same thing, and 9/16. Okay. So we're going to write this whole thing in terms of 32. So denominator 32 times 2 here. So we have 18 minus 9. And that's 9/32. We have plus, plus, plus this whole thing here. And that's exactly the same. So we have now, so this I'm going to write by symmetry of the triangles. This is also 9/32. So we have 18/32s, and we just simplify the whole expression and we get 9/16. And that is the area, well, the probability that the event, so the event that A and B, Alice and Bob, are not meeting.